Good morning, and thank you for joining us for the presentation NEC 2018, what you need, 17, sorry, what you need to know, brought to you by AEE Solar. Before we begin, if you're experiencing any technical difficulties, please notify me by typing your question in the question pane of your control panel on the right side of your screen and click send. We will be having a question and answer session following the presentation. You're welcome to submit your questions at any point during the webinar, and we will do our best to answer as many possible questions after the presentation. There will be a brief survey that will pop up in a new window immediately following the webinar. If you can please take a couple of minutes to complete it, and we will email you a copy of the presentation. If there are no questions, I'd like to go ahead and start the presentation. I'd like to introduce our moderator today, Aaron Liggett, Applications Engineer with AEE Solar. Aaron, I'm passing it over to you.
All right, thank you. As Caitlin said, my name is Aaron. I'm an Applications Engineer for AEE Solar. I'll be doing the presentation today, so let's go ahead and jump in. So first, I'd like to start off showing the statewide adoption of the NEC 2017 code. Currently, 40% of states have adopted the NEC 2017 code cycle, with another 26% in process. So the top left map is what is currently, which states are currently adopting or have adopted the 2017 code. So all the states in gray. On the bottom right, all the states in orange are the ones that are currently in process as of June 9th, 2018 of adopting the NEC 2017 code. So, roughly over half the states, about 66% will be in the 2017 code shortly. So some organizational changes to the code. The 2017 code actually went into more detail and defined the PV system. So in previous code articles, there was confusion of what was actually included in a PV system. So they defined what is actually included in the 690 section. So hopefully it'll clear up a lot of discrepancies. They added a new definition for functionally grounded systems, which we'll kind of go into more detail, which has some effects on wiring, overcurrent protection, and other things that we'll look at. So there's also a few new articles that were added. 691 is for 5 megawatt AC systems, non-utility owned. We won't go into much detail on these on this article. It mostly covers, fence grounding, access to equipment, compliance documentation, allowing PEs to, if there's not equipment on the market that is available to be used with what they're looking for, a PE can review and provide approval. 705, we have a little bit of updates in the interconnection section, then a new section, 706 for energy storage, and another one, 710 for standalone systems, which is pretty much the old 690.10 section. We're definitely not going to go over everything that's included in the changes, but we're going to talk about most of the, what I feel is the important subjects. So this is just the revisions for the PV system that happens in the 690 section. Like I said, we're not going to cover all of these. We're going to touch on quite a few that I feel is pretty important. We're going to talk about the 690.8 section, but mostly a new means for calculating PV circuit currents. It does actually have 690.8 does add DC to DC converters clarification. So essentially what it says is any DC to DC converter, the source circuit current shall be the converter's continuous output current. And 690.8A6 says the output circuit current max shall be the sum of all parallel circuit DC to DC converters. So we're not going to talk too much in detail about that, but I felt it was good to just kind of bring that to everybody's attention with, you know, SolarEdge, TIGO, all those other module level power electronic or DC to DC converters. Here are some revisions to 705, the interconnection section that pertains to PV systems. All right, so PV system clarification. The NEC 2017 clearly defines what is included in the PV system. For grid interactive microinverter AC modules and PV system ends at the inverter's AC disconnect. So they gave us diagrams. This is straight from the NEC 2017. They gave us diagrams in the beginning of the code article that clearly defines what is included in the PV system. So for the interactive, we have the PV source. Let me get the laser pointer. We have the PV source here that goes to the grid interactive inverter and the inverter output circuit to the PV disconnect. So this section right here is all that is included with the PV system. Same thing with AC modules or you know, microinverter type systems up to the first disconnect. Multi-mode AC coupled systems. So this is a battery system with AC coupled. It's very similar to grid interactive systems. The PV system ends at the PV system disconnect after the interactive inverter. So there was always a lot of confusion about if 690 pertained to, you know, what part of the battery system. There was always confusion with AHJs and, you know, with system designers. So hopefully this will help clarify what is included with 690, which would be the interactive inverter, the PV power source, and the first disconnect. And batteries are now under code 706, and multi-mode inverters will be included under the interconnection section. Multi-mode DC coupled systems, which is essentially a system, a normal battery backup system with a charge controller directly connected to the DC bus. In this system, it's the power source. It doesn't actually show the charge controller, but it could be interpreted as an array disconnect on the PV side of the charge controller. So, you know, they don't give us too much information here on what is included and what is not included, so that could be up for interpretation with the AHJ. I would definitely start communication with the AHJ to find out, you know, what they're kind of expecting and, you know, discuss these articles with them. Standalone system. For standalone system, the PV system ends at the array disconnect before the first device. The balance of the standalone system now falls under Articles 706 and 710. So this is very similar to the DC coupled system that we've seen previously, except for being standalone, not necessarily operational with any other or grid connected. So one of the biggest changes in the NEC 2017 was the functional grounded. So previously we would say transformerless inverters were ungrounded, or transformerless inverters were ungrounded and transformer inverters were grounded. Now they have made the change that essentially they operate the same. And actually none of the transformers that we've used, well, a very small amount of the inverters that we've used have been actually grounded. So now there is no difference between the two in the code, which will simplify things for your inspector. So what this is saying is a functionally grounded PV system is a PV system that has an electrical reference to ground that is not solidly grounded. So all of the inverters that we've been using for like the last decade or so have fit this criteria. There's really no difference between the two, and since there's really no difference, the majority of the systems are functionally grounded, and this now eliminates section 690.35 ungrounded PV systems from the code. Conductor color markings, colors and markings. So section 690.3B1 permits only solidly grounded conductors to have white or gray outer finish per 200.1. So now that we're using inverters that are actually functionally grounded, nothing is solidly grounded, the code actually does not allow us to use white or gray on the DC side. The NEC doesn't have requirements for conductor color, except that conductors should not be white or gray per the 690.3 or the 200.6, or green or yellow or bare per 250.119. So essentially, common practice has been use red for the positive, black for the negative. You have to be careful when you're doing this. Red can actually fade to a whitish looking color, which could cause issues later. A lot of times people will just, use 2 black wires and just tape, red tape, so many feet on the conductor to identify it. 690.31D, multi-conductor cable. Jacketed multi-conductor cable assemblies listed and identified for the application shall be permitted in outdoor locations. The cable shall be secured in intervals not exceeding 1.8 meters. I believe they added this in here for a lot of rapid shutdown devices use multi-conductor cable. For instance, SMA requires a 5-conductor cable between their initiation device and their rapid shutdown box. So I believe they just added provisions since seeing more multi-conductor cables used for rapid shutdown initiation devices. Inverter installation and retrofits. So section 690.3C1 now clarifies that installers may use either PV wire or USE2. One thing to be aware of is white USE2 on existing arrays if you're going to do a retrofit for an existing inverter that's on there. If you do a retrofit and you're actually pulling a permit to do that, you actually won't be code compliant if there is white USE2 as the negative conductor. Another thing to be aware of is USE2 is typically rated for less than 600 volts or less than or equal to 600 volts. So if you're doing a commercial project with 1,000 volts, be sure that the conductor that you're using is rated for its use or rated for the voltage. Section 690.9, only a single overcurrent protection device on either pole of the array, as long as all devices in the PV system are the same polarity. So essentially, you can put overcurrent protection is only required on one pole as long as it's the same polarity on the system. So as long as it's all negatives, you're fine, or all positives, you're fine. In section 690.15, disconnecting means are required in both legs of the PV circuit. This is the same requirements in previous versions, so not a huge change there. One other quick side note, with USE2 wire, verify that your glands and your strain release on your MC4s are correct for the jackets. Typically, PV wire, with it being double insulated, has a larger jacket diameter, which means that MC4s, if they fit PV wire, they might not necessarily fit USE2, which would lead to water ingress. So be aware of that with your MC4s and your strain release. So section 690.11, arc fault, mostly unchanged, but now there's an exception. Not really a huge benefit to grid-tied systems because we're required to have arc fault. Probably the biggest benefit will be DC coupled battery-based systems, just because they have limited options for arc fault equipment. Another nice thing is the exception that they put in. If the building is actually housing like a power shed to house your equipment, it's not counted as a building, which means that you do not have to have arc fault in it. So a lot of the off-grid guys or battery-based guys that have all their equipment in a power shed would not be required to have arc fault. Rapid shutdown. So this is another large change of 2017. I'm sure everybody has heard or had a little bit of details about this so far. 690.12 rapid shutdown has changed to an outside array boundary of conductors 1 foot from the boundaries are required to be controlled, and more than 3 foot from point of entry must be less than 30 volts in 30 seconds. They are also including an inside array boundary, which conductors located inside the array boundary must be limited to less than 80 volts in 30 seconds. So that pretty much limits us to module level shutdown. There's not very many modules, if any, at least up-to-date modules that you could series 2 together and stay under 80 volts. They don't really specify if that is, if you have to correct voltage correction for temperature or anything like that. So they don't say if you can use STC VOC for this situation. But this is not a requirement until January 1st of 2019. But likely it'll be module level shutdown for most systems, and probably through some sort of MLPE or some other device similar to SolarEdge type, Tigo, Enphase, and other manufacturers will be implementing something similar, I assume. The code actually does specify the initiation device shall be located at a readily accessible location outside of the building. And the equipment shall be listed and labeled for providing rapid shutdown. So previously it was identified, which means you could almost use off-the-shelf equipment as long as it was not outside of the scope of the use or the equipment parameters. You could assemble items to qualify as a rapid shutdown device, but they're pretty much saying now that it has to be labeled and listed for rapid shutdown use. Compliance. So they give 3 different types of ways to comply with rapid shutdown. The first is to have the entire array field labeled as a rapid shutdown PV array by NRTL, or module level shutdown performed by MLPEs, or if the system is installed with no conductive parts and, essentially using BIPV, building integrated PV parts with no exposed conductive parts, installed no more than 8 feet from exposed ground conductive parts, or ground shall not be required to comply with 690.12. Just a side note, the module level was not required until January 1st, 2019. So here's a quick comparison against NEC 2014 and 2017. So initially, the NEC 2014 code was a 10-second shutdown to 30 volts or less, and a TO was submitted to relax that to 30 seconds. So with the NEC 2014, you have a 10-foot array perimeter and 5-foot penetration into the building where it could be 600 volts. And then the controlled conductors had to reach 30 volts in 30 seconds after the TO was submitted. NEC 2017 is the 1-foot array perimeter with 3-foot penetration through the building. Now inside that perimeter, within the 1 foot and the 3-foot penetration would be required to be less than 80 volts. And then the controlled conductors leaving the array are required to be less than 30 volts. There's labeling changes from 2017 versus 2014 labeling. New signage is used to clarify multiple variations of rapid shutdown. So there's technically 3 different types of rapid shutdown: no rapid shutdown, 2014, rapid shutdown in 2017. So different labeling is required depending on which code you're building to. So string level shutdown is the red label on the left, which essentially says that conductors leaving the array are essentially a safe voltage. And the one on the right, the yellow one, is for the module level shutdown, essentially saying the array has been reduced, or reduced shock hazard in the array, as well as the conductors leaving the array itself. Buildings with more than one rapid shutdown type, which will likely be encountered more so in commercial, I would say, but possible in residential, you would need a placard showing the 2 different systems with the 2 different types of rapid shutdown. So as you can see on the label, they have part of the array highlighted and with a dotted line with red strings going through it, indicating that it's NEC 2014 PV array, so that it's above 80 volts. And then to the right, it's kind of a orangish yellowish color, saying that it's 80 volts or less in that array boundary. .690.15 DC disconnection. So you must have the ability to isolate all devices from conductors that are not solidly grounded. So this is, I think, definitely going to have some challenges with the AHJ and interpretation. But for circuits rated less than 30 amps, isolation non-load break devices can be connectors or fuse holders, disconnects are not required, but can be used for isolation. So this is saying that pretty much anything to just disconnect that string is fine, and if it's not load break, you can actually just mark it to say, or as long as it's marked, or you can mark it to do not disconnect under load or not for current interrupting, it would be fine. So anything MC4 finger safe fuse holders, isolating switch that requires a tool to open, anything like that would be allowed. Now the less than 30 amps is where it gets a little tricky, I think, because if you do the math backwards from 30 amps and you use 690.8 A11, which is our 1.56 multiplier, you're looking at roughly a module with 9.6 amps short circuit current. So, and that's really probably under the wattage class that we're currently using now. So it's going to be interesting how that actually will work out. So, you know, if you have 2 strings that you're combining, are you required to have a disconnect? For circuits over 30 amps, disconnecting means are required for isolation. So, you know, what that sounds like is if you're doing any type of combining, you need to have a disconnecting combiner, essentially. It could be local or remote operated. So if you're combining, depending on how the interpretation is, but 2 or 3 or more strings, and coming down to the inverter, it would be required to be a disconnecting combiner. And still only fusing is required on one side, either the positive or the negative, but both conductors must be disconnected. Right. Voltage and current calculations. So this is what I talked about briefly with the 690.8, but this is another means for calculating this. So systems greater than or equal to 100 kW, professional engineers can use simulation software to calculate max voltage and current. So 690.7, this allows us to use either the table in 690.7 for the voltage correction, or the manufacturer temperature coefficient on modules with the low temperature, and now adds in other provisions for using simulation software to actually model the system and look at maximum voltage that they will see on the system. So, you know, it's possible for larger commercial systems that you may be able to get an extra module out of this to help reduce stringing, labor, whatever else comes with that. And 690.8A12, the highest 3-hour current average based on local irradiance. So a PE can use simulation software to simulate the system and look at the PV source circuits and model what the amperage is, or what the conductors will see, or what amperage the conductors will see per local irradiance. So this current value shall not be less than 70% of the value calculated using 690.8A11, which is our standard method, which is just the module ISC times 1.56. So this value cannot be less than 70% of that. So here's a quick example. If you have a module, ISC rating is 9.49. The standard calculation method in 690.8A11 would be 9.49 times 1.25. Actually didn't include continuous duty rating in here, so that's why I'm only using one of the 1.25 multipliers. So that would have to be added in after. The simulation yields 3-hour average circuit current is 8.6 amps. If the system is smaller than 100 kW, the circuit must use the standard method. And also it must not be less than 70%. So 70% of our calculated method, or calculated from the A11, would be 8.3 amps. So this is saying that our source circuit conductor can be sized based on the value by the simulation software of 8.6 amps. So you could essentially see in larger systems reduced wire sizing for your PV source circuits, which could drastically reduce cost. There could definitely be a lot of benefits from it. So Article 705, interconnection. One of the biggest changes is to center-fed panels. So 705.12B23D allows the use of the 120% rule to connect to either end of the bus bar on center-fed panels, but not both. There actually has been a TIA that's submitted for this. So if a state does not adopt the NEC 27 code with this updated article for center-fed panels, the TIA is in place for adoption for HJs that have not adopted the 2017 code. It's TIA 14-12, center-fed panels in dwellings. So another change is 705.12 D6 has been removed. Its arc fault on AC wiring for microinverter systems is gone. There really was no arc fault breakers that would work for those circuits, so they ended up just removing it from the code article. Article 706, energy storage. So here they talk about energy storage systems as 3 different types: self-contained, pre-engineered, of matched components, and energy storage systems others. An energy storage system that is self-contained is assembly from one source that is listed as a complete assembly. So this would be something very similar to in-phase battery, LG Chem, power walls, something similar to those. The energy storage system that is pre-engineered is field field assembled of components that were engineered by the entity to work together. The components can be listed separately or together. So that's just something, you know, maybe similar to the IBR from Outback. Something similar to that, where each component is listed separately. An energy storage system other is composed of individual components listed separately. 706.5, all components other than lead acid batteries must be listed. Self-contained battery systems must be listed. So if you're using anything in the energy storage system other, they all must be UL recognized other than lead acid batteries. Lead acid batteries are only UL recognized and not listed. So they had to add this, that section in the code article. Article 706, energy storage. 706.7, circuit protection and disconnect at the energy storage system for circuits greater than 5 feet between the energy storage system equipment or through a partition still applies. So this was still a requirement in the 2014 code, but it is saying if your energy storage system is greater than 5 feet from the next device, you must have circuit protection and disconnecting means, which could be essentially the same thing. It could be a circuit breaker that you could use as a disconnect. This could definitely get challenging if you have a large system with multiple battery banks or stacked inverters, where you have multiple parallel cables. Having, you know, a disconnect that is able to switch that much current, you know, could be a challenge. 706.23a, all means of adjusting the charging process shall be accessible only to qualified persons. You know, there's not really too much clarification on this. You know, is a password adequate to prevent somebody that's not qualified from going through the system? I put an information note from the code that it looks like, you know, they want to implement this because certain types of energy storage, such as valve regulated lead acid or nickel cadmium, can experience thermal failure when overcharged. So, you know, if it's password protected, does that mean that that would be adequate and the AHJs will allow that? I think that one's going to be kind of up for interpretation. Maximum 100 volts DC now for dwelling units, or live parts not accessible for higher voltages. So you can use higher voltages. The LG battery and the storage, for example. The LG battery is, you know, 400 volt nominal battery, but it has protected, all the live parts are not accessible and protected, so it's allowed. So essentially it just bumped up the normal 48 volt to 100 volt DC. All right, Article 710, standalone systems. 710.1, the article covers electric power production sources operating in standalone mode. This is basically the old Article 690.10 brought over to the new article. Not much has changed here from the previous version. The article is very small. Not too much detail in it. Just talks about details of labeling for 120 VAC loads, or if you only have a 120 VAC inverter. Voltage and frequency control. And also one thing to note too is, so for these standalone systems, 690 only pertains up to the first PV system disconnect. And that's about it. So here is a few extra resources, some Solar Pro articles that are very helpful to that discuss a lot of the code changes. I always recommend having a copy of the NEC 2014 and 2017 available. I prefer the PDF version, so you can just use the search function. It helps out a lot. And also use your local AHJ and building department. I always like to start a conversation with them before projects get started, or if there's something strange that's happening on the project. You know, reach out to inverter manufacturers, and also we're here as well, and we have a YouTube channel with recorded webinars and presentations.
Perfect. Thank you, Aaron. So I'd like to go ahead and start off the question and answer session. If you have a question, go ahead and submit it through the question pane located on your control panel. We will again try to answer as many questions as possible. You can exit the webinar at any time during or following the question and answer session. The survey will pop up in a new window once the webinar ends. Give us your feedback on the survey and I will send you the presentation. I'd like to go ahead and start off with a question from Catherine. Prima County, Arizona, and most cities within county will adopt NEC 2017 later this year. In Arizona, AHJs adopt code, not the county. Is this typical?
It depends, really. I mean, everywhere is different, and it all really depends on the AHJ, and it can be from state level to county down to like local building departments can have varying adoption of code. So it's really, you know, if you're working in one county over and it's a different building department, you should really check with them because they could be on a completely different code article or even interpret the same code differently. So it's always good to double check, but yeah, it's pretty common for varying code cycles or code adoption in places that are even very local to each other. So.
Okay. So Rob has more of a statement, and maybe you can elaborate a little bit on this. You should note that new torque requirements in Section 110 AHJs all over North Carolina have latched onto the new section since the code panel did a study and found that 75% of all terminations are not torque to spec. Inspectors are wanting to see a torque chart as well as paint pen marks on the terminals.
Yeah, that definitely makes sense. I would recommend prior to installation, knowing what equipment you're using, they should have the torque markings in all installation manuals for inverters and racking. But definitely you should always stranded wire while you're installing it. Even if you torque it right off the beginning or right off the bat, usually the wires will settle slightly, and so it's always good to do a double check. So we would always show up, install the inverters and the electrical equipment, torque all the equipment, and before we left, we would do a pull test and retorque, and then mark at that point. But that's a good point. Thank you for bringing that up.
Great. Well, just drifting through here, it doesn't look like we have any other questions. So I want to thank you, Aaron. That concludes the question and answer portion of the webinar. Thank you all for joining us on the presentation. And join us on July 13th with Outback Power for the next webinar in our monthly webinar series, Outback Skybox Introduction. Check out our website for more training opportunities with AEE Solar. Have a great weekend, and thank you for doing business with AEE Solar.